Welcome everyone. Day 18 of Advent of Code is starting. This is Anagon Live, and please join me along the journey of solving part 1 and part 2, hopefully, on stream. And let's have a look at day 18 right now. Many worlds interpretation. It's very cool, by the way. Read about it on Wikipedia. As you approach Neptune, a planetary security system detects you and activates a giant tractor beam on Triton. You have no choice but to land. A scan of the local area reveals only one interesting feature: a massive underground vault. You generate a map of the tunnels, your puzzle input. The tunnels are too narrow to move diagonally. Okay. Only one entrance, marked with at, is present among the open passages, marked as a dot, and stone walls. Okay, but you also detect an assortment of keys as shown with lowercase letters and doors. Keys of a given letter open the door of the same letter. Small a opens big A, and so on. You aren't sure which key you need to disable the tractor beam, so you'll need to collect all of them. For example, suppose you have the following map. Okay, so I think we have to find the key and then open the first door and then go to the next key, open the next door, and so on. Starting from the entrance, you can only access a large door A and a key small a. So moving toward the door doesn't help you, but you can move 2 steps to collect the key and unlocking A in the process. Oh yeah, and A just disappears right away. Then you can move 6 steps to collect the only other key, B. So collecting every key took a total of 8 steps. The only reasonable move is to take A and unlock A, then do the same with B. Yeah. Now you need to choose. E is closer. Collecting it for now would be slower in the long run than collecting key D first, so that's the best choice. Finally, collecting E to unlock E, and then F, and so on. So hold on, let's look at this example. So we are here and we have a choice between key E and D. We do need to reach D in the end, so we can basically first go to D and then take E, open E, and then reach the door D, and then we reach F. Okay. We collect key E to unlock door E, yes, and there are a few more examples. And I must say the keys are very hard to read, but let's use some color coding in our output to make it a bit more readable. Shortest paths are 136 steps. And here we have another example. Okay. How many steps is the shortest path that collects all the keys? Okay. Let's do that. This definitely sounds like A star, the search algorithm that can solve this optimally. And I want to use A star today. So we have all of our input, and we are reading now all of the lines. So we can start with a grid, which of course will be a default dict with init. Yeah, I keep using less and less grids these days. I like to have dictionaries with positions in it, and maybe I can even just make it a list. So let's go over every character in the line. For C in line, so those are all the lines, so I first need to look over the lines. Although technically what I could do, of course, is I could actually iterate over the dimensions, but I don't know the dimensions, so I'll just do it like this. And then what? We're going to save a grid. So grid. Yeah. It is nice to actually have a dictionary there, so we can store some information for every position. So we have an XY position, and we'll store in that C for now, at least for now. And let's see, Y is 0, and every time we go down, we increment, but after the line. And here we just use enumerate. It's a bit more clear. So enumerate the lines so that we get a Y position, and for X we do the same. And then we have our position, and the @ sign should basically be a dot, but yeah, it's not that important. And so player, let's call player, that's where we are, that we now have as none, but if we find a character that is an @ then player is going to be XY. And then we need to know the location of the keys. I think that will be handy. If C is in a list, maybe we can do something like this, or range. I don't know if we can do that. A range between A and Z. Probably not. I think we have, yeah, we have only 26 keys. So let's just type them. That is not too hard. Let me see the EFG. Let's see if I did not make any mistakes. I did. I'm trying to be super fast here. Yeah, that's 26 of them. Looks almost correct. Yeah. And then we have a key. And the key is, I'll index it by key and then keep the position where it is. And we also want one case for the doors, and the doors are actually, yeah, the doors are capitals, and I don't want to detect keys as doors. So I need to uppercase this, and I don't have a function for that. I used to have a nice plugin for IntelliJ, but I don't have it in PyCharm. Okay, there is the alphabet again, and we keep it indoors. But maybe, to make it easier, I'll keep the lowercase version of the door, so that we can match the doors and the keys very easily. Hey Gord __. Is Advent of Code a good way to learn a new language? I think yes, if you don't mind to spend a bit more time to figure out how the language works. I think Advent of Code is a great way to practice learning a new language. I did this last year with Kotlin. I did in the end switch away from Kotlin, but not because the learning didn't work, but because I wanted to be faster, and I felt personally that it wasn't the fastest language for me. But you can definitely learn a new language with Advent of Code. I need to lowercase my string, and I'm not sure how to do that. Okay, actually it's just lower. Okay. So lower. Now we have the doors. And which language are you going to try to learn, Gord? And which language is the language you're most familiar with? Okay. Python, alright. And you mostly use C++. Oh yeah. I don't know C++, I've not programmed in it. I know the type of language it is, but I wouldn't be able to tell you if learning Python would be hard or not for you. I think Python is a much higher level language than C++. So you might need to get used to not managing a lot of things. And you've already started. Okay. Yeah. Well, if you already know some basics, I think you definitely can start. You're just gonna read a lot of documentation. And do ask questions on the stream if you have any Python questions. Okay, so we've parsed everything. Let me print it and see if we get a grid, player, and the keys and the doors. Yeah, of course the grid is going to take up all of the space. And maybe I'll actually use debug mode to visualize it a bit easier. So these are the doors. Yeah. And we have the keys here also. We should have 26 of them, and we do, but we have only 25 doors, so that means I made a mistake in my alphabet. Yes, I missed the letter M. Okay. I'm glad I am checking this very carefully. Alright, so that's it, and now we need to kind of decide where to go every time. And it's always the choice between going to the next key on our to-do list or to go to the nearest key on our to-do list. Oh man, but of course you could also, let's go to the whiteboard and draw out some situations. Well, let's say you have door A, B and C that you need to reach, and you have I'm gonna use a different color because for some reason red has been the underappreciated color in online video compression, and it always looks choppy or pixely. So A, B and C, and we have keys A, B and C. Let's draw it like that. And let's say that let's say it's connected all like this, and we are here. Now of course what you need to do is, now you have only one choice basically, and it's going to go to A first, so this example might not be very helpful. But let's say A was here and B was on the right, and here was nothing, and we had C here. But that might be a very interesting case. So what is now the fastest way to go and get all of those keys? So you would pass A, and then you can decide to either, oh no, that's not a good case, because then that means that A is already open and you need the key for B. So in that case you would definitely have to get B first and then go here. But I guess maybe I should come up with a different case. Okay, maybe the case would be where you have a key A here and a key B here and a key C here. Now what would be the fastest way if C was here? That's not so clear. Well, I guess getting all the keys and then going there. Well, I'm not so clear about it. Maybe that means that we can just make a search algorithm that tries out different orders, different strategies, and we can just calculate the cost of doing that. And we'll just do it that way. So for every search algorithm, we have a to-visit list. So we have to visit, and that is a list, and because we're going to use A star, that list is going to be always sorted. And an always sorted list in data structures is called a priority queue. So I'm going to look up how to use a priority queue in Python, and that one seems to be called heap queue. And heaps are binary trees, okay? That is actually not something you need to care about. You can push things on it and you can pop things from it, and you will push the smallest item, push an item and pop always the smallest item. So for example, okay, here's an example of implementing heap sort. That's not really what I was looking for. If you use tuples for your elements, then Python will already sort them by the first element in the tuple. That is super handy. So we'll use heap queue, and heap queue, maybe we need to import it. It can be. And I'm looking at the Python documentation for Python 2. So we need to look at Python 3. And that one is called queue. So it's called queue, and it is from, how do we use it actually? Queue.queue. Okay. And if you don't have a queue ready implemented in your programming language, you can just use a list and sort your list every time that you're going to pop from it. We're going to import it. Okay, and we have to know which places we have visited also, and that is going to be a set. And we need to, what else? I think that's it. Yeah. And for the visited places, we need to keep track of how many steps we've taken there. So maybe what we can do is turn this into a dictionary at some point. Let's see later what we will need to keep track of for every visited location. So that means for every search algorithm we have a to-visit list, and we are going to work it, process this list as long as we have items on it. And this is not a list but a queue, so I think I need to use a function rather than just checking the truthiness of it. And let's see if empty clears it or returns state. It returns the state. Okay. So while not empty, we're going to pop an item from the list. And that is not called pop, it's called... What is this? We have put. And what else do we have? Get. Okay. So we use get. And get should also remove it, I hope. Get, remove, and return an item from the queue. Oh. So we are visiting a certain location. Let's call it target. And then at every step of a search algorithm, we need to see which other locations we can visit from there. Find other locations, and after that we're going to evaluate whether our target is actually the goal. Check target is goal, and then we can break, and that's it. That is actually the entire gist of it. But now the trick is, how do we sort our queue, and how do we determine, yeah, for A star you need to estimate how many steps you've taken. Well, that's actually very simple to do because we can just keep track of it, and we need to estimate how much work we have to do still. So let's first find the other locations. So we are going to have to visit a location first, right? And that location is going to be the location where we start out. And let's keep there the player position, just like that. And we also want to keep track of what is our journey so far. And at that point, we have basically made 0 steps. And we might need an estimation for how much we have left. That probably is the case. For example, what we could do is, so what we want to optimize is the number of steps we take, and how much we have to do is how many keys are left. But it's not just a matter of 5 keys or 6 keys, it's a matter of how many steps do we need to still do to get all of the keys and all of the doors. So that's something we can keep track of. And maybe that's what I'll do right now. So steps left, it will be a function that calculates how many steps are left from a certain state, and that state will need a list of found keys, I suppose, and it needs to have a position, and using only that we could technically figure out how many steps are left. And I would say that yeah, I'm going to definitely test this function before we continue with the rest. So it would look like this. We start with well, hold on a second. Yeah, we will put the player position in it, and found keys is nothing, and then let's print that. And here we will just we'll just wait with this piece of the code. So for every key that is not found yet. So we have all of the keys that are not found. Let's look at the items then. So we have the key position and the key. Like this. And if the key is in the found keys, then we can skip it. But otherwise we'll need to keep track of the number of steps left. And the number of steps left is at least the Manhattan distance from you to the found key, to the unfound key. So the Manhattan distance, that would be basically we can explode position into x and y, and we can do the same for the key. We have key x and key y, that is the key position. And so the distance to the key is, well, let's call it dx and dy. So distance, or delta x and delta y, that is the absolute of x minus key x plus the absolute of y minus key y. So we count both dimensions. So that means that, for example, we are here on our grid and the key is here. Then the minimum distance we need to travel is like this, right? So that would be minus 10, for example, but that is of course an actual distance of 10, and also 10 here. Total distance will be 20. Alright, so I'm not sure why I'm working with dx dy, because that's not what I need. It's basically just the distance to key already calculated at once. And then the number of steps is the distance to the key. But that is the kind of as the bird flies or something is how it's called. So let's call it the minimum distance to key, because it might be more. And of course we're gonna have doors in between, and we're not gonna go straight. We're gonna have to walk around the walls, but this is definitely the minimum number of steps left. I'm going to indicate that also with minimum number of steps left. And having an estimation function that gives us the minimum number of steps required, that makes our heuristic going to be optimistic, because what it estimates is always less than what it really takes. So it means if you're very optimistic, you're going to explore a lot. And if you're pessimistic, you're not going to explore options that might be good for you and that might be better for you. So A star is an optimal algorithm that can really skip bad options and first try good options. But for that you need to be optimistic. If you're not optimistic, you're going to miss the shortest path. So those are the minimum number of steps left, and we need to return it. And let's see what we get as an output. So at least we're going to do 1214 steps to reach the goal. Now I want to be sure that there is no other target on the map except for keys. It looks like not. So now what can we do? What can we do indeed? I think, okay, we have our loop, right? Let's continue with that. So we are starting out with the number of steps left for this position, and that is going to be saved here. My queue was unimported automatically. So let's see how that works. Let's break. I don't know what I can do to break a loop without breaking here. Like I want to break after it. Well, I guess what I can do is just break on it and then just run one iteration. And I see also that our queue is already empty because we did not break. So I think that this is not the right way to initialize the queue. I think we probably have to do something like put like this. And now we actually break. So we have our target, and that is the target position. Let's call it TPOS, or maybe I'll just call it TXTY, and then the other part is going to be steps left. And actually, I just realized that our priority queue has to be sorted by the total number of estimated steps. So that means that if we want it to be sorted, the number of steps should be on the left and the player should be on the right. And we want to add to that also the number of steps we've taken, and that is 0 actually. And that is not necessary here, but I'm just writing it to remind myself that there are 2 parts involved in the steps left. And that means that also this is not the steps left, but the minimum total steps. Okay. Now, what is going to define our steps? There are going to be different ways to do that. And the reason is that we have to decide on where we're going to go, but also we're going to have to decide which key we're going to get. So let's say we are here and there are a few keys, like we have a key A right here and a key B right here, and we have a door A, let's say here, and a door B here. Now, of course, the steps that we can take literally, like if you don't think about anything else except for which steps you can take, then that means we can take this step here to go up, and we can go right and we can go down. And if we just do only that, just basically going in a direction and then letting the search algorithm figure out which direction brings us closer to the goal, that's something we could do. But that means we have no strategy at all, so we don't actually think about do we still need A and B, or do we need C? Like, for example, if you know that let's say there was another key, well, it couldn't have been called C, but let's say there was a key called C here and we already had it, right? So if we already had this key, then we don't need to go to C. We don't need to go here at all. So going up in this case would not make any sense, because the only keys available to us are going to be A and B. So, but our stepping estimation function does take into account that specific situation, because we are calculating the distance to all of the remaining keys. So that means that if we are going to the right, we're going to be a little bit closer to both A and B, and a little bit further away from C, but C is totally unimportant. So I think we actually don't need strategy. We just need a good cost function, and that's it. Well, that is cool. I see no one has solved the puzzle so far. So maybe this is a tricky one and it won't work, but we'll see. So the other locations that we are having are basically every other position around us. Every other position around us that is not a wall, that is, and that is not a door. It's also important. So we have 4 directions that we can go to. Let's call them dirs, and we can go, let's make a template. We can go to the right, -1 means to the left, and -1 means up if it's the second dimension, and 1 means down. How do I make a for loop run x times in Python? Well, the easiest way to do that, and the most common way, is to use range. So for x in range and then 0 till how many times you want to repeat, like that. I think there is no repeat function in Python per se. You're welcome. So that is all of the directions, and let's check if we can actually visit those directions. So for every direction in theirs, we need to know the new x and the new y, and that is the target x. Well, wait a second. Tx, yeah, this is something that confuses me sometimes. Tx is actually the location where we are, I would say. So even though I call this list to visit, it is kind of the base for where we are going to explore next. So from the list we get an item to visit, but actually it's not like we're gonna try to go there. It means we are there already. And that's why we're also starting with the player position, which is 00. We are there. So to visit is maybe not the right name. But let's see. Let's just keep it like this, but we have to keep it in mind. So it's x plus the dx for the direction, so let's unpack it, dx dy, and new y will be the y plus the dy, and then let's see if that position is available to us. So we have our grid with the new position, and let's see if that is actually an empty space. That means that we can explore it. And that means if we're gonna explore it, then we're going to put it on the to visit list. And what we're gonna put on it is, first of all, the estimated cost, estimated path, or how you call it, minimum steps left for this direction, and also what else? The position. So that is nx and ny. That's it. Now we just need to calculate how many steps are left. And actually that's not the steps left, but the minimum total steps, right? Because we're going to prioritize paths that have the least estimated total length. So we don't want to go for the path that is the most near our target solution, because that means we're going straight forward and never trying anything else. We're just gonna go forward and forward, and we want to try alternatives also. If we take a road that seems to be not really working well, that we're gonna try another road until that one seems to be the most slow one. So the total number of steps is the number of steps we've taken so far, and I didn't store that yet. Yeah, that means that maybe it's nicer if we keep the number of steps so far separately in our to visit list. So that means that first we have steps so far, and then the minimum steps left. But we have also a function for that. And so how do we solve this? Maybe we can call it get minimum steps left, like that. And the total steps of exploring in that direction would be the number of steps plus 1 plus the minimum steps left for that specific position. Get minimum steps left for the new x and y with and then all of the keys that we found at that point. So that is something we probably also need to keep track of in our to visit state. The keys, found keys. So we need to also know which keys we found at that point, and that is nothing at that point. Found keys. And now, of course, what we could do is, if we are not going to find an empty spot by the key, then we're going to append that key also to the to visit list. I think I will handle that case also. Let's say that, yeah. So either we have an empty spot or grid, or maybe let's extract this into a variable called tile. If the tile is empty or the tile is in the keys, so the names of the keys, then we are going to do this. And in case that we found a key in this position, we're going to append that key to the list. So, well, I'll use found key as the way to do that. And found key is actually an empty, is nothing. Or maybe let's use a list for that so that we can just append them. And so we have an empty list if we didn't find a key, or we have a key if we did find one. So we get a list of tile if the tile was in the keys list, and otherwise an empty list. This might be a little bit weird to read, but basically I want to append something to all of the found keys, and to do that we need to append a list, because if you add two lists, then they will be appended, or like created into a new longer list. And if we find no key, we'll just use an empty list. So those are the found keys for that particular step, and that's it. And the doors we cannot access, so if we have a door, we're not gonna do anything basically. And then we need to check if our target is the goal. But maybe let's first run this once to see if the code is behaving as we're thinking. So let's actually print something, print everything that we're keeping track of for our loop. So we are in the following position. We have just printed everything, and it says not enough values to unpack. That means that probably I misplaced a bracket, which I did. So it should look like this instead. To make that a little bit more clear, I'm going to use new lines. Then you can see a bit more clearly what is in this tuple. Yeah, maybe like this to make it a little bit more compact. Okay, so checking if our target is the goal. So if our xy equals, maybe I need parentheses around that. Wait a second, I think we don't need to check if our target is a goal, because we're not looking for a particular target. Well, we are kind of. I think key Z is the goal. Maybe that's what we can do. So if the grid at position xy equals z, that means that we found the last key, right? Then we're done, and we can break. And now I'm thinking, when do you need to check your goal? There's something important about that. I mentioned it before. If we check our goal right now and we found the goal and we're breaking right away, what that means is that yeah, what does it mean? If we're breaking right away, but there were some other options we haven't tried yet, we're not sure that this is going to be the best one. So how do you avoid breaking out early in A star? There was something about when you check goals, but I think this is probably correct. Like, if you check the goals while checking the areas around it, then you have a big problem. Ah yeah, I think I might know. I'm not entirely sure. I'll just break and I'll say found the goal, and maybe it is going to be maybe it is going to be the first one, because of the way of the priority queue, that we're always trying out the best paths first, but I'm not sure. So we have an issue with unpacking here. We have 1, 2, 3, 4 items in our list, and here we have 1, 2, 3, 4. But what are we adding when we are adding something? We are adding only 2 items, so that is definitely a bit too short, and we need to keep the number of total steps, but that is not correct. We are actually splitting it into the number of steps taken plus the total steps left. So that's the minimum steps left. And we keep track of our current position. That is nx and y. That is the third item in the tuple. Oh, we have it already. And then the found keys. And oh, I see that is a bit strange. I'm passing it to the minimum steps left, but I also need to pass it to the visit list. Let's call it new found keys. That is going to be this one. Oh, we're passing that to both sections. Okay, now let's rerun it and see where we are. Not enough values to unpack, so I still do something wrong. And that is in this location. Maybe before we actually go over it, we can do a visit.get and see what we get out of that. We get 4 items, and I see that we have the steps, which is the first one, minimum steps left. Then we have, oh, we have a list of keys actually instead of the position, so I reversed it by accident. Oh, are we running? Yep. So what happens now? Our first visiting location is going to be 40 and 40, and we have 0 steps made and these many steps left, and we're going to continue. And actually I don't want to keep looping forever. I want to see how it works, how we're actually going to check out every direction. But nothing is happening. I have a breakpoint here, but when I run it, it doesn't break. Why is that? That doesn't make a lot of sense. Maybe this breakpoint is fake, it doesn't work. Well, strange behavior, I would say. So we're going to explore all the directions, and we found out that our tile is actually a dot. And so we're going to see if we want to go to 3940, and we are. So then we have our visit list going to be expanded, and we'll run it 1, 2, 3 more times, and then we're going to end up there. And now we're visiting the second part, and that is we've made 1 step and we have quite a few steps less remaining. Still found no key though. And maybe what we can do is also visualize our grid, or we just keep it running and see if we just get an answer. Maybe we just get an answer. Today is quite tricky. Yes, it is tricky. If you can apply a star, it's fine. Emily, how is breadth first search for you? Are you familiar with that, and do you know how to implement that? Because basically a star is like breadth first search, and all you need to do to make it into a star is kind of keeping your visit list that you're going to go over to keep it sorted in some way. Yeah, so you have a list of positions to visit, right? And now you're just going over it breadth first search by putting everything to the end. Yeah, so instead of putting it to the end, well, you just put it on the list and then you sort your list by some kind of estimate. And maybe I'll let you think a little bit about what kind of estimate, but you need to make sure that the first item on your list is always going to be the best option that you can imagine. And there's a small requirement that's a formal thing, but it is important, is that you don't underestimate your remaining steps. So that means you have to be overly optimistic So, well, I'll let you think about that for some time. But basically it's just like BFS, but you sort your visiting list. Let me know if that helps. Alright. Good luck. And by the way, if your estimate includes only the steps you've taken so far, then that's basically Dijkstra's algorithm. And if you include the steps you have remaining, then you get an A algorithm. And if you are sure that your estimate is overly optimistic, then you have A star. Okay, so it's looping and looping and looping. I think it's going to take a long time like this, and I have no idea if we're getting anywhere. Especially since I don't see any keys being found. That is also a bit of a problem. So let's run it without debug mode on. It should be a bit faster. Here you see we've taken 12 steps or so. Maybe I don't want to output at every iteration. So let's say that max steps is 0, and we'll just keep track of the max steps, and every time we have a different one. Let's say every time we made it one step further, then we're going to print. So the maximum steps is the max between steps and max steps. Actually like this, if the number of steps we're taking is bigger than the max steps, then we're going to print it, and we're going to save it also. So now we should get something like 1, 2, and so on. So we've taken 11 steps and we still haven't found any key, so that doesn't look very right. I'm going to... I think I'm going to print our map. Let's print our map. So we have the grid and we need to know the dimensions. And the dimensions, we can just take them as... Well, actually, that is the cool thing. We've added them in the list. No, we didn't sort them really. Well, what we can do to print is actually loop over y in. Maybe we can loop over x and y in the grid's keys, which are sorted. If they are sorted by x position first and then y position, that's not exactly what we want. Maybe we want to sort it first by y and then by x. So let's say y and x for x, y in keys. Now we've reversed the x and y position and we sorted them, so now we are going over them by row, and we can print whatever is in the grid at position x, y. And oh, but then we're not gonna have breaks, we're not gonna print the row. How can we solve that? Okay, maybe it is a bit easier to actually loop over the range, the entire range. So for y in range from the minimum x, the minimum y and the maximum y. And I want to calculate that before. This is something I'm doing like in every other puzzle. So I think it was the same on day 17. Do we have it? Something like that? Yeah. You see, it's basically the same many times. So we have our grid keys. We're going to take the minimum by taking here the first position and here the second position. And this is something irrelevant right now. So now we know the min and the max, and we can sort, we can loop over the range from the min y to the max y, and then the same for x. And my algorithm is still running in the background, by the way, and it is only at step 16. That is not a good sign. That means that probably the sorting function doesn't really estimate helpfully. I'm not sure exactly why, but let's see. Alright. We're gonna print it. We're gonna print whatever is in the grid at XY without a line ending, and then we'll print a new line. And I'll just print every step for now. Let's do that. Maybe our current position. Yeah, we're actually not updating the map at all, and maybe this is actually a problem. Maybe that's the problem. I'm not sure. Not sure if that's a problem. We also have an @ sign, and if you have an @ sign, that means what? That you cannot go over it. That is fine. And I see another thing that I forgot about. We haven't looked at the set of locations we've visited. So that means that you are actually able to go in circles and circles and circles. Of course, A* is not going to try to do that because the steps are going to increase ever more and ever more. And that is going to make it a less of an attractive option. So I'm not entirely sure why it's not progressing, but maybe once we actually print everything that we get a better idea. The only thing is, if we have our robot at a certain position, then we can't actually see that. So XY is our robot or player or whoever, and so I'm overriding that by accident, and I want to keep those variables intact. And I want to make sure that if our XY position is the same as where we are, then we're going to print something else. We're going to print an @ sign with no line ending, and otherwise we'll print whatever was there. And also, what is this? I think I need some parents around it. And also, when we actually visit the grid, yeah, you see here I'm detecting an @ sign, but I'm not storing anything in the grid. Well, I am storing a C, but I want to store a dot so that we have an empty space there. We might need to go over it again. So now we've changed a few things at once. That is not a wise way to work, but I'll use it for now. I'll do it like this for now. So we have an extra max around here that we don't need. That looks a bit better. Now we get a huge output, and maybe we should actually break. Let's break every time. So we have a lot of things on the screen, and I want to make sure that we see something more clearly. So let's extract the tile here, and the tile is this one, and in day 16 we were able to print, no, it was day 17, we were able to print things in color, I think. So let's see how I did that. That is with a special character escape sequence. Okay, so if our tile is in the keys, then we're going to use yellow. Then color is going to be yellow. Well, this is actually not yellow, this is going to be red or something. Let's see how that works. The output character, let's call it O, is going to be this, with the tile as a string parameter, and else our output character is going to be just the tile, and we'll print it. Now let's see if we actually get some more readable output. So we do not see any kind of change. So is it the case that we actually don't recognize any keys? Maybe. Oh, we do actually go over that. So we have found a tile which is an M, and it is in the keys apparently, and we are using that. So let's see if we actually see that in the output. So we have printed it now already, it's at the very end. But I must say, I don't see it. Here is an M, yes, but the color doesn't look any different. Maybe what we should do is emulate a terminal. I'm not entirely sure. I do need to do that sometimes. And I'm going to break again here. So we printed the tile and then we should have at the very end something in color, but we don't see that. So maybe it's because I was doing 31 instead of changing the code here. Yes, that's it. I think it should be 33, then an escape sequence and then another one. Well, that still is surprising that we don't get something in color. Maybe it's just that print doesn't work for this particular ANSI escape color escape sequences. So I'm using print here also. It seems to be fine. And so why? And I was using 92 and here I'm also using 92. So that doesn't look too bad. Maybe it could be the problem. Let me run day 17 and see what we get there. If we also see colors. Yes, we do. You see, it's nice and bright red. Alright, so why? 92 MS and then to reset the color right after, and we're printing that. And in our output we cannot see it. Maybe for some reason it's not picking up the new changes. Sometimes I have feelings that it's not running the latest version of my code, which shouldn't be able to happen, but okay, that also didn't happen. Maybe I can... Maybe Python strips those when rendering the dictionary? I wouldn't think so, because I'm just rendering characters here. Oh man. Oh, this is so silly. I'm printing the tile instead of the overwritten output character. So there you go. Now we actually see it as an M. It's gold, it's not super clear. Let's look at ANSI escape sequence. And we have it on Wikipedia. This is going to hurt your eyes. Especially when I reach this part. And the escape sequence for the background color is 103. And for the foreground color, that means that you can basically append them. I want to use black, so background yellow and foreground black. So let's run it one time, and now we should get something that is very clear to see. Yes, it is. And my output looks a little bit different. I'm having orange here because I have a theme with different colors. So those colors are not literal. And then I want to also keep track of the doors, and I'll make them red. That means that if the tile is in, or if the uppercase of the tile, no, hold on a second. So if it is an uppercase, then it's not going to be in the keys list, right? Because uppercase is a door. So if I use elif, that means that I'm going to be able to check doors here. If I did it the other way around, it wouldn't work, because I saved my doors with lowercase letters, and then we would just detect doors every time when they are actually keys. So a door I'll visualize with red in the background and maybe white in the foreground. That is 97. Like this. And there is always bright also. You can use bright yellow and bright colors. I'm not sure if they are actually more bright or less bright on my screen. Because you also have yellow here, but on the standard example it looks kind of dark. Well, let's see. And then if we are the robot, then I also want to make it a little bit more clear. So we're always printing in the same way, and for the robot we're going to print an add sign which is blue. Let's make it blue. So that is in the foreground I like to have 96. In the back that is the cyan, and then in the background I want to have 104, that is deep blue. And now we have no attribute called key because I made a typo. Now we get our output and our robot is right in the middle, so that is working fine. And the doors are not shown on the screen, but that didn't work. Maybe I didn't actually save the doors with lower cases. Let's see. I did do that. So that means that... But hold on. On the grid they are still uppercases. Okay, so I have to actually lower the door tile before that would work. Okay. And now we have doors, but for some reason they look up, they show up as gray. So I think I mistyped my background color, or my terminal settings are not right. So I used 100 instead of 101. That is why. Now we get something that is a bit more readable, but it's still hurtful on the eyes. So last step, and then we'll really continue to implement it. That is going to use white as a foreground color, but in my terminal white is black because I use a black background. That means that I think I should use the color 40 as the foreground color. No, 30. That is black, and that might show up as white. But white is kind of unreadable also. So that makes it a little bit confusing, but for doors let's use then yellow as the foreground color. And for the yellow keys we'll use red as the foreground color, I guess. Yeah, let's do that. So it's 91 and 93. So they're kind of inverted versions of each other. Well, that doesn't look exactly readable, but I think I'm going to keep it like this because I don't want to spend all of the time. But I must say I really can't read. I can't read it really well at all. So let's use then maybe 0, which means the default. Let's see what we get from there. Nope. Nope, nope, nope. Our nice music has paused. YouTube does want to save some bandwidth here and not kind of let it keep going on and on in the background. Okay, I know what to do. I'm not gonna use the background color, I'm using only the foreground color, and that should also make it work. Let's try it like that. Yeah, actually that was the easiest way to do it. Sorry everyone if that was a bit boring for some time. So we're starting there in the top and we're going to explore, but it's such a huge grid that I think I'm going to not print everything. I want to print basically 5 up and 5 down from the robot, maybe, or maybe not. Maybe I'll just keep it as it is for now and show it in a separate window so that we have a little bit more space. And the puzzle is very clear, so we don't need to look at it all the time. So it's going to be like this, and it almost fits in. No, it doesn't fit in the screen. Make it a little bit more small. The console font is going to be a little bit smaller. This maybe. Okay, and this big list that we're printing here, I think we don't need to do that. That is this one, and then we will just rerun it. Okay, there we are. And it's hard to see, but we are in the middle, and then we're running another iteration. And then we'll be on the right, then on the left, then on the top, and then on the bottom. It's interesting to see already that It's trying out all 4 directions at once, so it sounds like the step estimate for the robot is going to return the same results for all angles. Otherwise it would have started right away going near a key that is nearby. And now we're back at the start, and we're going up and down and again in the middle and up left and down right, down left. So our estimation function is really not working, or our sorting function is not working. Let's actually print also, or have a look at how many steps are left. So we printed our location and we didn't actually print our current state. So I'll just do that like this, because I want to know at every step, like really, what does it think, how many steps are left? Does it think it can improve just by moving? Maybe that means that our priority queue is sorted the wrong way around. So we'll run it. At first, total number of steps should be 1214, and then we'll continue. And then every time we make a step, we're actually a lot closer to every other key. That's what it thinks. But I see that most of the keys are on the right. Or maybe not. Maybe not, that's not really the case. Okay. So number of total steps left is 1224, okay. And 1208. So it should really kind of continue with the best option every time. I'll print it at the bottom. Maybe I'll print it twice, actually. And with 2 new lines in between to make it a bit more easy to read. I see no one has solved. Oh, I see Alex has solved part 1. Nice. So that's the number, and I want to print also the total number of steps, because that is actually what counts. Total steps is like this. 1214, and then 1205, 1225. But why is that? We should not actually go over. Ah, I know. Because I decided to split up my steps and the minimum steps left, now my steps is actually the first item in my tuple. And because of that, my priority queue is sorting first by the number of steps that we did. So we'll always try out paths which we haven't walked on much yet. So I need to keep the total, the minimum total steps separately as well, because that's what we're going to sort by. So the minimum total steps when we start is the minimum number of steps left. Let's calculate it before. The start minimum steps left is going to be saved here, and it's going to also be here as a total number of steps remaining. And when we append to the queue, we're going to add those 2 values together, and now I think we should get a much better result. So here we have our break statement, and we are at this middle position, and we're going to the right, and now we're going to the left to 1225. 1209 sounds better. 12. How do we know for sure that it's exploring better? It's when you try out something that you think was going to be very great, and then when you tried it, it wasn't actually. And that means that you're going to jump to different positions. So far, it's not so clear yet if it's really following a logic. So it keeps kind of going back in circles. It keeps thinking that the first position was the best one after all, but now it starts to go to different positions and it starts to jump around a little bit more. So that is a good sign. Yeah, and we haven't found any keys yet, so maybe I can keep running it. Oh, by the way, we need to keep the number of steps and not exactly the number, like all of the paths that we've taken so far. We can do that. Maybe I'll do that. That is actually fun. It's not necessary, but it would be very much fun to do that. So I'm going to keep the path also in the to visit list, and the path will start out being completely empty, or actually it will start out with 0, 0. That is our start. No, our start is the player position, and every time we're going to take our path from the visit list. I'm not sure why I did this. It should be path, and then we're going to add to the path our current position. So that is just doing it like this, x, y. Now we've added it, and then we can say here in our search or in our printing function if our current tile that we're looking at is in the path. Tile in path, no, it's about x and y being in the path. Then we can print it with a different color. I think that would be very cool. And let's use green, 92, like this, and let's run it again. Then we can see a little bit better what it's doing. I guess green is not 92, or it is 92, but I have to type it correctly. And maybe actually I'll check also if the tile is a dot, and then we'll just render it with a space and with a background color. Then it will be very clear. And the background color green is actually 42. I'm going to use a little bit of a less bright color. I sound a little bit like Bob Ross right now, choosing my colors, and I made a mistake. It should be a double equal sign. Painting ASCII colors on the screen. So how does it look? So we went left, up and down, and then we're going to explore a bit more. And I'm going to... Yeah, this takes a long time. I want to actually do 10 steps or something. Maybe I want to keep running it without any breaking. And let's see what it looks like. Well, that looks like a lot of steps. A lot of things going on. I will look again at this part where we say, did we increase our next, or did we improve our steps further? I'll call it false. If we have more steps done than before, then we went further. And although our goal is not necessarily to go as far as possible, we need to know how many keys we get. So actually, I want to keep the best number of keys that we found so far, and it's 0 when we start. And if we actually have more keys, found keys is more than the best number of keys we had so far, then we are further. Further is true. And if we're further, then I want to print the map. Like this. If further, then print this entire thing. Let's go. So that means until we find the first key, we actually won't have improved, but I can maybe I can also keep track of if we found more steps, and that is what we are checking here. And then if we have no keys, then in that case we can also render it there. So if we have no keys at all, we can write it like this. If we have not found any keys, and we are doing more steps, then we'll also be further. Now we can kind of render it. So a lot is going on. We are not actually getting any further, it seems. But it is doing a lot of work, but why does it say we're not getting any further? We have the max steps that we're keeping. Okay. So why is that not working? Okay, I feel like there's a lot of things going wrong. I'll also keep track of iterations, and I'll just add one to every iteration. And when we have 100 iterations, then I'm also going to render the screen. So if I modulo 100 or maybe 10 is 0, then we're going to render. And let's run it again. So now we do see a lot, and I'm not sure why this further logic that I made doesn't work. Maybe it's because I'm using an AND instead of an OR or something. So either we have found more keys than before, or I have no keys found and we do have more steps than before. It should kind of work, but it doesn't. So we are back to the start because we were going up, and then it looked like when we went down it was better than before. So that is not very logical. And I'm a bit surprised that this is happening, because we do have an estimate function that should sort everything based on the steps taken plus the steps left. And maybe it's because I'm taking into account only the keys and not the doors when I'm estimating the steps left. That's actually what I do. So estimate visiting the keys, that's what we're doing here. But we're not estimating visiting the doors. And also, yeah, there's a few things that I missed, and I'll show you right now what that is. So what I missed is that if we are here and we have a key here, and a door here and here, and the number of steps that I estimate to go should actually, of course, include all of the distances to the key. But you know, going to this key means that you end up here, and then the distance to the next key is not going to be this. And what the distance is going to be, you don't know. It depends very much on the order in which you visit the keys. But what you can say for sure, that at least it would be the distance of going back to where you started, and then from there to get the next key. That is definitely that is not the minimum steps required. That is an overestimate. And we want to make underestimates, right? Or do we want to make overestimates? Oh, I'm not sure now. I'm not sure now. If we make an overestimate of our steps left, that means that we might be near the goal position and we think we have 10 steps left, but when we finally make it, it means we are done. And then looking at all of the other options that were overestimates, they will all look less attractive than what we found so far. On the other hand, if you underestimate, and let's say you're 5 steps away from your goal, no, let's say you're 1 step away from your goal, but you are thinking that you're 0 steps away from your goal. When you actually make the step, it took you 1 step, but all of the other options that would reach your goal, you think they might be only 0 steps. So you're going to try all of them also before actually stopping. So we do need to make underestimates, we do need to be overly optimistic. That is correct. But of course, the better we are at estimating, the better our results are going to be. So if we have 2 keys that are really side by side, what is the minimum we need to go that we know for sure? We cannot just like roughly estimate it. We are not allowed to be ever pessimistic. If we're ever pessimistic, then we're not gonna get an optimal outcome. So what do we know for sure? And this is definitely being pessimistic to count this twice. So that is not working. Well, what we can do is look at the first key in the list of keys that we need to get. So we have all of the keys here, and we need to get them in a certain order, right? Well, let's say it's A, B, and C. We know for sure that we must get A to finish the puzzle. And it might be the case that B and C are very much nearby it. But maybe we can just look at the distance to the nearest key and see how that is. So the nearest key or the nearest door that is open. Maybe something like that. And also I have not thought about the algorithm where we open doors. So we also need to keep track of if there's a door but we have a key for it, that we can actually go on it. That's something that I am missing now in my implementation. Yeah. Well, we're definitely overestimating our distances. So that means that every time you take a step, it was much better than what you thought you were gonna do. And that means that you would just keep walking just for the purpose of walking, because as you walk, your total estimate is gonna go down if you're going a little bit near keys, I think. I'm not entirely sure. Another thing we could do is just look at the nearest key and use that as the minimum distance that we need to do to reach the end. It's not a very good estimate, but it is an estimate that we can do consistently. So let's do that. So instead of looping over all of the distances, we're going to take from the keys the first item. Well, let's not take the item, but so we are, let's say we're sorting that, right? That means we're sorting by the tuples and the key goes first, so we'll get A first. So key and position for key KP in items, and then I only want to return that. Not sure. Oh yeah, we have to make a tuple of that explicitly, and only return it if the key is not in found keys. So only the keys that are left we're going to evaluate, and then we're sorting it by the key, and then we'll take the first item from that. That is the next key that we need to find, and we'll take the distance to the next key. Manhattan from A to B is like this. AX AY is A, and BX BY is B, and then we'll return this. I'm just putting it into a function because I'm a bit tired to always write it over and over. AY and BY. So then the next key is there. We also have the next door. The next door might also be important. So we have a door here and the door position, and we want to take only the doors that we have not found yet. So we can basically use found keys for that. Your first approximation looks simple enough. Looks at score. Second approximation must be a tough one. Yeah, indeed. So we have only 2 of our participants who have solved part 1. So it is definitely not one of the easier puzzles. But if you do look at it, it doesn't seem too complicated. And right now I also feel like it's not too bad. Now I'm not sure if I should take the distance to the next key and the next door and add them together. I think probably not, because if you have a key that you need to find and it's here and the door is right afterwards, then the distance is not really twice that distance, right? It's just going to be this one once and then plus 1 for the extra step. So I maybe actually a minimum distance that we're going to have to take is not the distance to the first key that is on our list, but the distance to the furthest key or door, whichever is closest. Because we're gonna have to go there eventually, right? Yeah, we're gonna have to get there eventually. So I wanna have the key distances as a separate list. That is going to be a list of we're going over all of the keys, key in, and maybe the position also, or key KP in keys of items. Yeah, I think the algorithm of the estimation function is really the core of this puzzle. We want to have a distance, and that is going to be the first item. Now we can nicely use the Manhattan function here. So it's from the current position, which is the player, till KP. Oh, actually that is called position. Yeah. So from position to the key position, those are all the distances to the keys. And the distances to the doors are going to be door distances. And that is going to be a D, and this will be a door. We'll go over the doors. That is the door, and we need to sort them like that. And so we're going to take the furthest one out of those. So that is the key dists, the last one, furthest key. Because this is a puzzle that does involve a lot of thinking, I'm going to be very explicit again about my variables. Normally I might, well not normally, during Advent of Code I'm doing a little bit of less explicit writing, but now I think it is helpful to do it very cleanly. So we have the door dists -1, and we want to take the distance only, and that is the first item. And yeah, basically that means we don't need any of these other positions, but I'll just keep it for now. We might need it later if we're optimizing our estimation function. And then we'll return the maximum. Does that make sense? Maximum of the, well, the steps, right? That's the steps we're going to return. Yeah, we're going to take the maximum number of steps out of those two. For the furthest key, the steps are in position, oh, that's already there. And then the furthest door key. Well, we definitely have to do that, at least, to get anywhere in this puzzle. To go to the furthest key. And we have a lot of output going on. And it looks so far that we're really not doing a lot of useful work, and I'm still not sure why it keeps going back. Maybe, yeah, what is actually going on? So when let's look at it really slowly, step by step. So we are starting here, and let's print every step of the way. So we do divide by 1 instead. Right, so let's see how it's going. So we start here, and now I want to know all of the lists, all of the items that we have left to visit. Can we do that? Can we actually print that? So to visit is a priority queue, and we cannot actually, we might be able to peep, which means to have a look without popping it. Maybe we can do that with what is full. Actually, full means if the queue is full. Oh, okay. And what else? Task done. Max size. Maybe we can look that up in Python documentation. Python Q peep. Or peek is actually called peek mostly. Examining items in a Python queue. It was specifically created to use threads. However, by examining source code, you can see that it simply uses collections.dq, a double-ended queue, which can easily accomplish your task. You may index the first item and pop left in constant time. Okay, if that's the case, then I'll use dq instead of the queue that I was using before. So here we'll use a dq, and then we need to use pop left instead of get. And a dq can pop from the left or the right, so you can get the lowest or the highest. And what was said in stack was you can index the first item just using the index operator. Okay, so that means that we can have a look at the best places to visit in 2019 for vin to visit. And let's slice it from 0 till 10 and print all of those places we might want to visit. And like this, print v. Maybe I'll add a little dash to kind of indent it a bit. Collections.dq does not have an attribute put, so we need to use something else like append, yes. And also here. So it does implement a sort of list interface. That is handy. Not sure why the other queuing library doesn't implement it. And it doesn't have an empty. So clear, maybe not. Length, no. Okay. It seems like there's no way to check the length, but maybe we can just use it in this way. Yeah, len is actually... Oh. It says return len self, but in the implementation I don't see anything. That could be that this is not the implementation, this is just a kind of helper for PyCharm to show you how it works and give you help. I'm going to run again. And what just happened? Nothing happened actually. Why is that? I have break statements? No, I don't have any break statements. And I also don't get any prints. Why is that? So len is not possible. I have to do... Yeah, I do have to do len like that instead of not. And then we cannot use slicing. Okay. Then we'll just use an index. For 0 till 10, we'll check to visit v. And one more time. Index out of range, okay, but we can check the length, so we can do the minimum of 10 and the length of to visit -1, so that we don't overshoot it. Now we get something, and we have printed all of the to visit items, but now it's empty, so that makes sense. And then the second time we have the following options to explore, and those options are actually going down, going left, and going up. And our estimation for all of those features is actually the same, and I'm not sure if that makes sense. Are we estimating from the new position? New x and new y, that's what we're using. And new x and new y is actually changed, okay. It would be very hard to believe that our estimation is going to be exactly the same. Because, well, if there is, how could that be the case? If the furthest one is actually a different one when you go to the left than to the right. That could be, well, maybe the furthest one is the one on the top left if you go left, and the one on the bottom right if you go right, and no matter which way you go, either you're actually I see. Okay, if you go left, you're going one further from the right, but one closer to the left. So the furthest one is still going to be the same, maybe that's the reason. And I also know that I noticed now that until we reach the very furthest key, we're actually not going to improve our estimates. Our estimates are going to be constant. Although we do get closer to the furthest key, I think this is not really a good approach in general. So I'm going to change again my implementation. I want to use the distance to the first key that we need. And I was using that before, wasn't I? Or was it only an attempt that I never actually finished? Yeah, I never actually finished it. So we'll take the first key on our to visit list, and let's see if the next door is available. Then we're gonna go to the door, and otherwise we're gonna go to the next key. So if our next door, which has a position and a door, so that is the first item. If our next door name is in the found keys, then we're going to return the Manhattan distance to that door. That is a very good heuristic. Next door 1 from our current position, and otherwise we're gonna go to the key for that door, which should be the same, I think. So then we're returning the distance to the key. Okay, let's do that. And remember that it doesn't mean that we're always going to go to the first key and always to the first door. It just means that our step estimation function is going to use that as a basis. So if that actually doesn't turn out to be the fastest way, we are still going to explore different ways. And what is the problem here exactly? We say list object is not an iterator. That sounds very weird because list is a sort of iterator, isn't it? Maybe it's not. Maybe I should not use next. And I should just use an index like this. I'm not sure if this would work. Yes, apparently we can run it. And it is running really quite violently right now. Because I'm not breaking at all. And let's actually wait after printing those options and restart. Let's look at the output, and so we have nothing to try. And from the last position that we were in, we are going to we have these positions left, and the one we just took was this one, I think. That was the previous position we looked at, and now we actually do get some different estimates. So there I just played it again by accident. Let's actually look at the output and see where the robot is gonna go. I do see that it's going back to the start quite regularly, and I think that is because of the estimate function being very rough, and going back a step is such a small cost, just one extra cost, that it doesn't kind of make it a worse option than trying something else that seems quite expensive. I am going to keep track of the positions I've visited and add them to the list. So every time we append something to visit, we're going to append it also to the visited list. No, I will append it to the visited list. Will I do it when I look at the children, or when I actually explored it? That is a good question. Because right, we can visit a certain space in multiple ways, and we always want to explore it in the quickest way and not the slowest way. And we are using a step estimation, a cost estimation function to prioritize our queue. And it is overly optimistic, but it might still not be accurate. So it might still be that I know what we can do. We're going to save after we visited a location how many steps it took us to get there. So it is a dictionary. That's really after visiting it. That is right here. So that is x and y equals the number of steps, but we'll only override it if it's less. So it's like the least steps. This one keeps the least steps to every position. And I do realize now that this is completely unnecessary and irrelevant, because we are going to visit every position more than once. We're gonna have to, because we need to take keys and go to other doors and open them. So we don't want to avoid going over the same key, same position, but we don't want to go over a position with having exactly the same keys as we had before. That really would not make any sense. So what if we keep track of the visited locations with the number of keys that we had at that point? So position plus number of keys, like as a tuple. Let's do that. And I think we can just keep it as a set. And again, if I want to store some more metadata, then I will turn it again into a grid, into a dictionary, excuse me. So what we are gonna visit here, that is visited. No, it's not visited yet. I'll just do it here. So our steps after we have taken a look at this position, then we're saying that we have visited it. And that is a tuple of x and y and the length of the found keys. That is really all we need. No, we can have different keys, but still the same number of keys. So I actually want to make it into a set. Is that, can you hash a set? I'm not sure about that. Let's check that out quickly. So let's say we have a set called x, which contains 1, 2, and 3. So x looks like this. Then let's see if we can use x as an index. So this. Oh, come on. X as an index, like this. Unhashable type set. Okay, so that doesn't work. But what we can do is we take the sorted list, sorted x, and use that as an input. That also doesn't work. So we must sort it first and then make it into a tuple so that we have our different combinations of keys always in exactly the same way. Those are the found keys, and we have the new found keys here, and we're going to not append it if the found key is going to, if that exact same combination was already evaluated with smaller steps, with bigger hold on. What if we find a way to reach that position with less steps than previously? Then actually we would like to evaluate it, right? So that means that we can keep the number of steps, and so we're going to keep the tuple here, and then we'll keep the number of steps. There's some extra parentheses somewhere. Here should be x, y, and number of steps. Maybe I'll actually make a tuple around the position to make it a little bit more clear. So there we go. That is the number of steps we've taken there, and we need to check if it is really smaller or not. So visited key is this, and if the visited key is not in the visited list, or the visited list with the key as a index is smaller than the number of steps, then we're going to store it. Gee, you're saying you have one path, but now you have to do it for all paths. Is that for step 2? the part 2 of the puzzle, or is that just something you need to do to find the quickest path? Well, it's good that you found one path at least. Okay, just for part 1. Okay, good. Then I know that there's no spoiler in there. So we're keeping the least number of steps. Yeah. And then if our new position that we might evaluate is smaller, then we can actually append it. So, but I want to look only at the number of steps and not the estimated number of steps. So that is going to be this one, next number of steps. And if the next number of steps is smaller than the visited locations with the specific key, and the key is made up of two things, namely the new x and the new y, and also a normalized or canonified, I'm not sure how to say that, a canonically made list of the found keys, and that is the sorted list, the sorted new found keys, and turned it into a tuple like that, not tuple but tuple. And if that happens, or of course let's extract it and call it new visited key, or if that key doesn't exist, then we're also going to append it. So let's check that the new visited key is actually not in the visited list. Then we're going to append it. Okay, now we should see our player going a little bit more smartly, trying out new positions rather than old positions and going back to the start every time. It's going very fast. I want to break after every step. So we have now looked at the center. We're going right and we're going left. We're going up and we're going down, and now we should not go to the center again. We're going to the top right and to the top bottom, left and bottom. So it's still kind of estimating the distance to the nearest key or to the first key in exactly the same way. And I think I misinterpreted something about the puzzle, which is that, as I can see from the puzzle right here, it's not necessarily that you have to start with key A. That's how it looks like right now. I can't really zoom in right now. Let's see what happens if I do this. Okay, that does do something. Okay, I'm a bit scared to do this because everything on my laptop is now enlarging. So the first key that we can actually reach looks like maybe U or something. We can go up here, but not right. Maybe it's Y. Y is the first key that we can reach. So no, that's a door, to be honest. To be correct, we cannot reach this place. Maybe we can... Where can we go? Where can we go? We cannot go here. We can go here, 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 and we can go down. And then we can go here. Man, doing puzzles like this by hand is a very different experience. And we can go down. Okay, this is like really a maze, you know. I think we're stuck here now. But maybe R is the most close one. Yeah, actually, we can reach R. So we can go here, 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 and reach R, and then open door R on the right. So that means we should not sort our keys. Well, we can sort our keys, but not when we determine what our next key is. So our next key is determined here. So we don't sort it. Let's just sort it. Oh man. We actually have no idea what the next key is going to be. You might say it's the nearest one, but you don't know. So let's try first to reach the nearest key and then all the other keys, right? So the sorted list is, we're sorting by distance again. So here we have all the keys that are not found, and then we're sorting by key. So we have two parameters. We have what we're sorting and how we're sorting it, and that we're using an inline function which takes a certain key or key with position, key item, and it will return for that key item the distance of that item's first element, which is the second element, which is the position, the distance of that one till our position, which we just called position in this function, and that is what it's going to sort by, and sort will go and make the lowest item the first one. So that would work, and now I have a highlight that says what is this, what is not correct about this. I don't see actually what is going wrong. Generator expression must be parenthesized, if not sole argument. That means that we have to put brackets around it here. And like that. And we do the same thing for the door, okay? So the door is here. We'll use brackets also. And someone, oh Gort, you are following me, cool, that is very nice. And we'll see each other again also tomorrow. And how's it going, by the way? How's your Python doing? You were asking me, how do you fix the error IO operation on closed file? That sounds like you are... I'm not exactly sure. Can you share how you're reading your file? Because if you're going to the end of your file and then you're doing another loop over your file, for example, you're probably already... your file handler is already closed. So you can't loop over the same file handler. Maybe that's you cannot loop over it twice. Maybe that's what's going on. That was it, okay. Well, glad that was probably helpful. So we're sorting also to the door's position. It's the same thing, except that now we are talking about a door rather than a key. And we'll use the first one. But you don't know what to do. So if you are doing a file reading, so this is the most clean way that you can read files. Using with, open, then your file as, and then something that will make a variable for you that gives you a file handler. And then when this code block is completed, the file will automatically close. That's one way to do it. If you don't use with and you just use open, like file handle is this, and you can do your for loop over the lines. That's all good. And then in the end, you technically need to do close. And then if you want to read the file again, you just kind of do again file handle equals open. That's I think what you probably need to do. But what you could also do is read your lines first, store it in a variable, and just loop over those lines for twice. Then you know you're not gonna have that problem. So where was I? I was doing very well. I was looking at the first key that is nearby, the most nearby key, and then the most nearby door. And then if we actually have the key for that door, we're going to the door, and otherwise we're just gonna go to the nearest key. And let's see if we are finally gonna make progress on this puzzle. So I think the nearest key should now be U. We can go here. We are actually able to reach it also technically. It is kind of far to the right. So it means that this R is actually closer. Let's see where we're gonna go. So now going down should be the best option, I would say. We are estimating our total distance to be 14 at the moment. And every time we explore, it's kind of is different. And what is the best option so far? Yeah, it's not so clear which key we're actually gonna visit now. We're trying a bunch of different things. Maybe the nearest key is actually on the top. I'm not sure. Yeah, that's not so clear. But we are making long lines. That is a good sign. So I think there are probably a bunch of keys that we could try to reach. Oh, what just happened? Okay. I'm gonna keep running this for a few moments and then pause it. Like this. We are actually exploring more now. And we could go here and it's... Wait a second. Oh, we're not gonna be able to reach R. Oh no. Okay, well, let's just keep running it and see what happens after some time. And if we have a key found, we definitely want to break. So we don't have a key yet, right? Here we don't have a key, but we are going somewhere. Okay, so that's what I'm going to do. I'm going to check again. I'm going to print every 100 iterations, or we are further. And then if we are printing, then I am going to break. And this one is still in our break statement. So we'll break in here and then just run it. And maybe when we break, we also would like to clean the screen. And we do that by using os.system clear or something like that. And we need to import OS. No. How was that? It was in day 17 that I did that. Clear. And Gort, you're saying, but now you don't know what to do. Well, what are you working on right now? Where are you in your puzzle? Are you doing also day 18 or are you doing a different day? You're doing day 1, okay. And day 1 was about the rocket fuel. You just started, okay, cool. You can always start, you know, you don't have to be right there from the start, because you can still get points, you can still enjoy learning all of the Python and the puzzles, even on a later day. I'm going to search in my code and look for clear, and it is os.system clear. Okay, so we call a function called system, and that is probably a shell command or something. Not entirely sure, and we'll debug it until we reach 100 steps or we reach a key, right? Or until we go further. So now we are a bit further, and now we are going further, step by step, and the best distance, oh, actually, the furthest distance that we are reaching is not always the same. Now we actually reached key R and we have it, so now I'm very curious what will happen after. Now, unfortunately, we cannot print dynamically now. We cannot say that we want to print, well, actually, it will still print correctly. So if we find a new key or we're a bit further, then we're going to print. Oh, now we have the same key twice. That is not what I expected. So how does that happen? So let's say that our new tile is NX and Y, and if the tile isn't the available keys, then we're going to just append it and we're going to try that position. Well, that doesn't make a lot of sense. And for the found keys, we're actually going to have to make it into a set as well, because we want it to be unique. Maybe we can make it like a set in this way. So we'll first make it into a set, and for the minimum steps left, we need to have a list, I think. I'm not sure if that can... Okay, that is actually fine if that is a set, no problem there. So maybe that would work. Then we're not gonna go over R again. So that's it, we'll run it again. So Gort, you just started and you don't know what to do. Did you understand the problem? Did you understand what you're supposed to calculate and the instructions? I'm making it again into a list because I feel like changing your data type suddenly is going to break some things. And here we have no typed system, we have Python, it's loosely typed, so you don't get like any compiler warnings. or changing some types. Sometimes that's helpful and sometimes not. So we're going to do a bunch of loops, and we've now found R, and we're now going up. You put the for loop into a with statement. Okay, good. It's an improvement. And now we're exploring further and we're not appending the key anymore. That is good. And we're still exploring, and now we basically need to go to R, right? To capital R. Or we go just to the nearest other key. That is also fine. And we'll need to figure out later if that was in the end shortest path. So, well. A lot of exploring. And we still haven't found another key. So I will actually halt the program only when we have more keys. And further, I have defined as either having no keys and then be able to get more steps, or just finding another key. But I'm also showing us a loop every time we reach, we have done 100 iterations. And I'm thinking about not doing that. I think I want to break only if we went further, but I am still fine printing it right now, at least. So let's, maybe we could just do breakpoint like that. Ah, that is very smart. So if we are further, then we have a breakpoint, and otherwise not. Like that. We don't need to use breakpoints anymore, we can just write them. Okay, well first we need to get to key R. Then after that we should actually be able to run it fairly automatically. And then we'll just stop only when we have a new key, or when we didn't have a key yet and we're exploring further on that side. Okay. Well, looks like we're still looping quite a lot. We're still breaking quite a lot. Even though we didn't get a key on the bottom left here, we're still breaking every time. And why is that? Further is true when we have more keys than before. Did I actually save best number of keys? I don't think I did. So that is actually a problem. Yeah. So if we have more keys than before, then we have more keys. Keys is, oh, more keys is true. Caps lock is messing up my typing. And that will be done like this, and we're going to keep the number of found keys. And then if we have not found any keys and we have more steps, or we have found more keys, then we're going to say that we went further, and then we can print everything. And why is this not okay? More keys might not be defined, of course. So let's do it like this and rerun. And you know what? Actually, I'm not going to break every time we have more steps. I think it's a little bit too much. Just when we have more keys, then we're going to break and show the map. So it still says we're further. Why is that? I did say more keys, right? Why is it breaking then? We're also breaking if we are... Well, what is this about? What is this about? Yeah, that looks a bit better. Okay, so we found R, and we're running a crazy amount of times and showing all of the options available. That is maybe a bit of an overkill. But I did think that we actually printed only the first 10 or so. Oh no, I did. Yeah, not sure why it's so many. Maybe because I'm printing the path and the path is just insanely large. So let's run it again. We found R, and then We found R and X, but we actually haven't been to any door yet, have we? We could have gone to door R, but apparently that's... maybe that was not the best thing to do. Who knows? Maybe we want to keep track also of which doors we visited, just to get an idea, but technically we don't have to. So in this case we found 3 options. This is printing really a lot of things, so maybe I'll just print it every 1000 iterations or so, just to make it a bit faster. So that was that, and we continue. And then my touch keys were not working for a second. And you're still getting the same error. Gort, could you paste your code perhaps on Pastebin or Gist? And I'll just look at it quickly. It's probably very easy to help me and won't take me a lot of time away from solving today's puzzle. So it is working. It is not fast at all. Of course, debug mode is on, and yeah, when debug mode is on, it can make it more slow. And now we are breaking because we found more keys than before. We have actually found 4 of them. And I want to know... Well, actually, we don't have to go over a door. Or, hold on a second. Ah, I'm missing something. Yeah, that's something I should have taken a note of. And that is, if we are looking at positions to visit, which is here, I'll add a note. Check locations to visit. And if there is a door, then we can't go there, right? Unless, of course, we have the key for that door. And so we can go, let's make that a variable. We can visit if the tile is empty or the tile is in keys. So it is a key basically. Or the tile in lowercase is actually in the keys. So that means that we are dealing with a door, and the door, the name of the door is also matching the keys that we have, and we have that key. So maybe I should do it like this. And we in fact have the key like this. Then we can visit it. Okay, that should make it better perhaps, because that means we can get key R and then pass door R also. And I want to make sure that I'm rendering the doors still. So only when the path is empty, then I'm going to render a green line. Otherwise, I'll just render whatever else was there. And I want to make the walls a little bit more visible also. Let's try to see if we can use black for that. So I'll use background code 40. So if the tile is actually a hash, then our output will look like the other one, but then we'll use the color for black, which is 40, and we'll use a space. Let's see how that looks. Well, it is very hard to read, so that doesn't work. Let's use white then. Let's see what white looks like in my system. It looks like I didn't change the right one. I had to do 37, I think. Yeah. And no, I have to use the background color, so that is 47 actually. And let's run it. Yeah, that looks a little bit better, a bit easier to read. And then we are going to use nothing in the case of having a dot. So if the tile is a dot, then we'll just render a space, a black space. Now actually our code, our maze is going to look so much more clear. Ugly, yes, but more clear. And I do see some errors actually. I do see that it looks like we're actually crossing some positions that we're not supposed to cross. And why is that? Before that didn't happen. So I'm not sure if I trust what I did just now. I'm going to commit this code, maybe. Maybe I'm gonna keep this little section and revert it. Because before, these kind of bugs didn't happen. Okay, I did add, of course, the can visit logic. So I think probably my error, if there is any error, should be in the can visit logic. So the tile that we're talking about is the end tile, the new tile. And here we have an assignment by accident. That is wrong. Maybe that was the reason why it didn't work. Yeah, this looks a lot better. And unfortunately, I don't really like the color of the visited locations. So if we are in path, then I was using something else. I wasn't using the background, very bright background color. I was using the dark background color, but it looks kind of the same. Okay, so let's keep going. We have 2 keys now, and now we have 3 keys. It's still not clear whether we actually passed a door. I think this is where we start. Maybe we should highlight the case where we have a door visited. Basically, we visited a door when it's in the path, so that's also not that hard to do. So here we're checking something about the path. If we visit it and the tile is a dot, then we're doing something. But what if it's a door? So it's in the path and it is a door. Let's see if we can check that in a bit of a more robust way. Is door is it's a door when the lowercase of the tile name is in the door keys, like that. So if we have a door, then we render it like a certain color. If it's in the path and it's a door, then we do something else. So we need to first check if it's in the path and the door, and otherwise we do something else. So if it's in the path and it's a door, then we're going to render it, let's say, bright magenta. So we'll use the foreground color 95 for that. And re-render it again. So there we go. So far I don't see any doors being purple. I'm not also seeing the entire screen. Doesn't all fit. Just keeps going now. So maybe this will work, it just takes a long time. If your A-star algorithm is taking too much time, it means that your estimation function is very, very optimistic. And that means that every time you explore, it turns out to be more expensive than you thought, and you're going to try all alternatives. So the way to make A-star faster is to estimate more closely to the actual cost. Yeah. So the most naive implementation would be to first go to the... wait. How would you know that? I was thinking you would go to the first key on your list, like keys that you can reach, and then reach the first... well, first go to the first key. Oh man, not sure I'm really getting it. So it is in theory a kind of simple problem, but it seems to be very complex. Like the computational complexity is pretty big, even if you're using a search algorithm. And you see now the screen is already stuck for a few moments, maybe a minute or so, and it's not finding any new keys. And it seems also that we're not actually exploring or passing any doors. Maybe that's the reason that we're stuck. Maybe Maybe we actually can't pass a door. Maybe that's something that isn't working well. So let's see about the door logic. So can visit, that is determined here. I will extract it into is empty or is key or is door. So is door means that the found keys and the tile is lower. Yeah, so we have the case where it's a door with key. So basically an open door, right? Is open door. Cannot use refactoring at the moment because I'm in debug mode. And maybe we can try to see if we are actually ever evaluating an open door. I realize something now. We're never walking back, aren't we? No, we are. We should be able to walk back. Because I do keep track of every position and how many keys you had there. And if you went somewhere with the same number of keys in your pocket, then you don't have to go there again. Because, yeah, the state is exactly the same. The same number of doors were open. So if we have an open door that we're checking, I want to actually put a breakpoint there to know for sure that it ever happens. And also what I'm doing here is I'm appending the visited location if it has less steps than what we visited before. Does that make sense? So we need to be able to visit it, and also it should have been visited with fewer steps, or it should not have been visited with those specific keys before. Yeah, that seems logical. I haven't really evaluated with the code, like by running it and looking at how it happens. I'm running it now here in the bottom to see. Oh, actually, if we run it in normal mode without debugging and we do a breakpoint, we actually are able to break it just using enter. That is cool. Although I'm not sure if it's doing really what I think it does, but let's run it here in debug mode. And now we do get we do get an open door, but that is not because it's a door, that's because it's actually a key. So we need to really check that it's a key, and it's only a key. Sorry, we need to check that it's a door, and it's only when the tile is in the list of doors, basically. But my list of doors is in lowercase, and I think that is really not helpful. I'm just going to keep them in uppercase. That means that in a few positions, a few places in my code, I have to change some things. So let's see where I'm doing lower in my code, and that is the place where I check if the door is open. So if it is a door and the tile in lowercase is in the found keys, okay, so this is done. Now let's look at any other place where I might do lower. Okay, so that is no longer needed. So if the tile is in the door keys, then we have a door key. And anywhere else where I'm doing lower? No. Then how about upper? Do I do upper anywhere? No. So we can now run it. Hopefully we are going to open some doors now. Going up, and we're breaking because we have found an open door. We have reached a position where we think we might have an open door. Hold on while I'm taking a sneeze. Just muted everything on time before I broke your ears. So we say that we have an open door and it's here. And I think that was actually a key and not a door. So let's look at previous position when we went down. So that was here. Then Oh, I don't see a door. Maybe are we rendering the door as an empty spot? So if we're rendering... Hey, I don't see my isDoor and isOpenDoor function. So... So if it's a door, we're not rendering right now. That's why. So we should render the tile still. Let's run it again. So do we have any doors? I don't see them. And do we render doors in general? If it's a door, we're just going to render the tile. Yeah, we do. And okay. And I do see a bunch of doors everywhere. So it looks like that part is going fine. But why do we think that we have an open door when we are here? Because that doesn't look at all like we had doors there from the beginning. So you see here, there's no open door. And what is this about? We have position. It says it's tile R. But actually, that one is here. Does that mean that our x and y coordinates are flipped? Is that what it means? That could be, of course. We are storing the grid coordinates using x first. That's my convention. We have a grid with x and y, and we first go over the lines, then over the columns. So that seems fine. Then when we're saving the positions, we're extracting with x and first. Here we're extracting with x and then y. Here also. So we have position 59 and 44. Well, it would be a little bit hard to figure out where that is exactly, but I can figure out how many lines it is to the right. So what I'll do is just to check out where is R, copy this and then paste it somewhere, such as in a plain text file, and then select it. So we have, before the R, we have 59 characters. And we say 59. So the X position looks like it's correct. And the Y position, I'm just gonna assume it's correct. So that's where R is. And now, why do we say that at this breakpoint, this particular breakpoint, we might have R as a consideration? And I know, and that's because we are looking already at the next iteration. So let's, at the start of the loop, print a horizontal line to show clearly that we actually, let's do it until for the full length. Well, doesn't matter. Let's say 100 characters. So yeah, you have to be very clear about what are you looking at. Are you looking at the map of the previous iteration or the current map? And here we see we print a whole lot of lines. That's not exactly the way I meant. I didn't want to do that. But I do want to see when we break, are we at the end of our iteration or not? And we're breaking right now. Right here. I'm just gonna rerun that. So here we have more keys. Now we have an open door. And we have an open door, but we haven't rendered yet. So basically, if we would go here, we would see the door being opened, kind of. I was a bit surprised to see the open door being triggered many times. It probably means that it didn't break at the end of the iteration as I hoped. So I'll do it one more time. And also, when we have an open door, I do want to print. What can we do to visualize the current state? Not entirely sure. Maybe we can extract this into a function. That is always a bit messy in Python. So what I'm going to do is Okay, let's say that our open door is false. So we don't see an open door yet, but then we are checking all the directions and then we found one. So if we have found an open door, then we're going to break. So I should do it like this. Is door, and that's actually going to be at the beginning of the checking of the new locations. So we have no open door. Maybe have, or maybe near open door. So like, let's do it like this. We're near an open door, and then if we're near an open door, then we're going to break like that. And are we always going to break, or are we only going to break if we are further? I think we're only going to break when we're further, but that might be fine because we're always further when we are reaching a new door for the first time. So we're now going to be near an open door, probably. But it says that we should near an open door a few times, and not sure how that can be. Okay. Well, let's run it until we finally reach the end of our iteration. Our iteration right now is actually, let's see that. It's 1744. And now we actually stopped. So we still are not breaking when we have when we are near an open door. Why is that? Or near open door, like that. So right now I seem to be mostly struggling with the different ways I'm breaking, and not so much with the puzzle. And now we should, yeah, okay, finally. So here now we say that we're near an open door, and that means we could actually kind of go over it. Maybe what I can do is, instead of using breakpoints, I will just use instructions like go to next key, or like stop until next key, or just do one step. I think that will be more helpful. So let's say we have run until, and first we'll run until we have, say, nothing. So run until none means I want to kind of configure when we're going to pause and show the screen. By default I want it to pause always. So if we have run until as nothing, or maybe stop condition is a better term. Stop condition, or maybe break condition. Break condition is always, then A or always. And that means that if we are breaking is, for different cases we have breaking situations. So if our breaking condition is always, then breaking is going to be true. And if our break condition is key, we're going to break if we have more keys. If our breaking condition is D, then it means when we're going to break when we have a more distance, or maybe steps for distance, S for steps, I mean. So we have a few options, and then we can see we are breaking, and then when we break we're going to print, and then at the end we're going to ask what is your next breaking condition. So we do a prompt or input with some text, I think, breaking or running until, and then we have the option A is single step, one step. K is next key, and S is hold on. S is when you go further. Maybe not so logical. Running until. Maybe I would like to do just a number of iterations. So one is one step, like N is number of steps. I'm not sure. Maybe I'll just keep it like always wait when. All right. So we're waiting when something happens, and let's see if that works. We run it. So, well, let's run it until we have a next key. And there should be some kind of separator there. And we haven't run until we had a next key, because probably our input is not saved. Break condition is this one, and we'll have to strip it, most likely, and rerun it. So let's run till the next key, and that did not really work. Seems like that. Rent break condition, and let's also put a breakpoint there. See what happened, and that's all. So let's run it until the next key, and our break. Okay, our break condition is K, and here we do have the breaking conditions specified. And that means that we should go until we have more keys. Maybe. We should do if breaking, not if break condition. Like that. So, K. Till the next key, please. We are breaking already to show how it worked. Can I post my leaderboard code? Again, of course. My leaderboard code is right here. So, yeah, you were not on the leaderboard yet, right? At least, if you are, I don't know with which username. You're adding now. Nice. You'll show up on the board in a moment. And everything else is going fine. Okay, we found one key, and basically I wanna go until a door as well, until we find the next door. So let's make another breaking condition. If break condition equals door, then we're gonna break if we are near an open door. And that would work. I guess that's all we need to do. No, we need to also remind ourselves what the options are. Alright, you're added and I see you. Alright, nice work, G. I'll add your name to my alias list a bit later. So now I want to go to near an open door, and that is triggering a breakpoint, another breakpoint, which is not relevant right now. And I did say D, and it's still running and running and running. And it looks like near open door was not really triggered. So are we near an open door? We are just iterating over all of the positions and checking for the open doors. That really should work, but not sure exactly why it's halting right now. Is it halting or is it running? It looks like it's halting. Oh yeah, okay, I still had some old breakpoints left over. We're still running the code. Welcome to the Cool Kids Club, indeed. So your code is running and you're waiting for it to be solved, is that right? So we'll run until a key, then till a door, and now we're at the door, and let's run again until the next key. And that next key is actually all the way to the top. And that means that we went to R, but we didn't actually find any useful thing to do there. And let's run again to another, until we're at another key. So we have a bunch of keys, and I am printing the data only after the prompt, and I want to show the prompt after we print the current state. So now we can, oh yeah, and also I want to do that if you don't provide any input. New break condition. So only if that one is actually not empty. Like let's say length is bigger than 0, then we're going to override it. So then I can just press enter and try it. So we'll get keys by keys. So we found 3 keys. And as far as I understood the puzzle, we don't necessarily have to open all of the doors. We just need to get all of the keys. But I'm assuming that there is a door behind which is 1 key, and we cannot access that key until we open the door, and that is actually the last key. So now we get an unsupported format character right here. I did something wrong here. Is 95 not correct? Oh, I have no S here. Oh, so that's actually a door that is opened, and we didn't show that so far. So key, another key, another key, another key. So maybe when we reach the 4th key, we are actually going to open doors. Yeah, I think my estimation function really should improve. Oh, this is going to look a lot better already. We have passed a door, finally. That looks cool. But you know, the problem is in fact that being near a certain key doesn't mean that you have very few steps left in the puzzle, right? Oh man. Because let's say we've collected 10 keys and now we're very nearby another key. Then it means we're gonna try to get that key like very hard. Or actually, let's say we have another state where we have almost no keys, but we're near another one that we can't reach easily. We're gonna keep exploring that other key, because all I'm doing now is looking at the nearest key and see how far that away is. So that is not very efficient. And you say you should test your code with examples first. Maybe that is the best hint so far. We do have examples, of course, and one looks like this. And let me also run my code on examples. Why not? Why start with the hardest puzzle? Example1.txt. I'm not sure if it's example1. Well, here is one. Starting from the entrance. Yeah, okay. That's the first one. Okay, my new file dialog is not accessible anymore. That's just a plain text file, and that is example1.txt. We're going to use this one and run our code there. So what happened, G? You're running your code on examples now, and doesn't it work, or is it actually working as you're expecting? So we are running in debug mode, and this is what it looks like. Okay, so the first problem I'm seeing already is that I'm not rendering the full image. So that is a nice result of trying out code on examples. Now we're gonna see more bugs probably. You run the final example and it got 81. So this looks good, right? Let's go to always wait and see what we're doing. Now we're opening the left door, and now we're out of range. And why is that actually? We are getting out of range here because we are looking for the next key. And can it be that oh, hold on a second. To get the minimum number of steps left based on the found keys, and we're checking all of the keys, all the key items that we haven't found yet. But what if we have found all of the keys? Then we have nothing to do, right? And we just need to go to the doors. So let's first check if we actually have a next key. So if okay, first the most simple case. If we have no next keys and no next doors, then we are done, and our remaining distance is going to be 0. Optimistically 0, right? And if we do have next doors to do, and the first next door that we're going to visit, well, we don't always have to go to the nearest next door, but this is only our estimation function, so it is a good minimum. Or let's look at all of the doors that we have keys for. Actually, that is it. We need to go to the doors for which we do have keys, not the doors for which we don't have keys. That makes no sense. So the next door that we haven't been yet, but how do we know which one we haven't been yet? So let's pass unopened doors. But no, we don't necessarily have to go to doors. We have to get to keys. This is the important part. You know what? I'm going to focus only on the keys, and the doors is just like whatever. I'm not going to focus on that. So if we have no keys left, then we're gonna return 0. And if we do have keys left, then we're gonna return the Manhattan distance to that next key. Next keys, then the first one out of that list. And ouch, the second example takes a lot of time for you. Okay, that's an interesting bit of info. I don't know how mine will perform. So it's going right, then left, then right, and then back tracing, and then trying out. Yeah, okay, it's trying to reach B, and we're just assuming that we can pass A, right? Now we're on A, now we're near it, and now we're at B. And then what happens now? We're going back, and we're back, and we're back, and we're just doing other things. And actually we haven't really stopped. So I do think that we found the quickest way to finish the puzzle. Let's see for a more complicated example if that gives us some insight. Example2.txt, and when we run it, what happens? Debug mode, and we'll go until we're always going to pause, and best option so far seems to go right, and then you get the next key, and then go to get the next key, which is there. And then we have C, and we can go left, don't we? Or we can get D, and it's not so clear at this point which is the better option, so we're trying out both ways actually, and that is fine. So let's say that yeah, we're still not sure which is the better way, so we can even try to go back to D, or we can go to D directly, and you're seeing just those two options competing with each other until it actually, well, it's going a long time trying those two options. And then in the end, I think it's going to be clear which one is faster, because now that D was reached, the next nearby item is E, and for the other one well, it's still not clear which one is faster. Yeah, the visualizations work quite well, thanks. So just what I'm doing is just using some escape sequences, and they're a bit nasty, but you can just look them up on any site and it will be clear. Yeah, how it works. It's not that hard. So we're still figuring out which is the fastest way to reach the next key. We actually have 3 different options now. But hold on a second, I think we've reached the last key, right? So we're done, and now we're just doing something funky, and that's it. Now we've explored every possibility. So I just hope that if we found the goal, that we can actually stop, that we can be confident in doing that. So the target is goal, then we're going to say we found the goal, and the goal is not when we reach Z, but it's actually when we have found all the keys. So found keys. Let's see which keys are remaining. Maybe if the length of the found keys is the same as the number of keys that we know to exist, and then we're breaking. So what if we run this all at once? And we're going to... When are we going to wait? Never. I don't want to wait at all. So let's do E for end. And if we have E, then we're not doing anything. So if breaking condition is E, this is not necessary of course, but I just want to make it explicit. Breaking is false. Well, maybe we can break when we are at the end. So that is known when we are here. So reached goal is going to be our parameter. Reached goal, then we are breaking if we reached the goal, and otherwise maybe G for goal, like that. Okay, let's run it again. I want to break at the goal, and now we're at the goal. And what else? You can reasonably solve it if you stop fighting the type system. You're gonna try it tomorrow. Alright, good luck then tomorrow. And thanks for hanging out, Fuzzy. We'll see each other again. So, well, time is progressing. It's almost 9 o'clock. We have spent a lot of time on this. And I'm kind of amazed right now that Zarankiewicz Alex has already finished part 1 and 2 in such a short amount of time. Let's see... what is actually the answer that we need to provide? I think it's the number of steps, right? The shortest path that collects all the keys. And when we reach the goal, I do want to print that we reached it. And we're going to, well, how to do it? Maybe we'll just break here. Yeah. Print reached goal in number of steps, and that is just like this. Let's go to the goal, and we reached it in 86 steps. That might not be the fastest way to do it. Let's run it forever. And that means that we need another breaking condition, which I call end, and that one will just always run. And then let's see how many goals we're actually finding. Oh, well, basically this is what it's doing now, is it's reaching the goal and then continuing on, and then every step afterwards we are still reaching the goal, so to say. So that makes no sense. I think what we need to do is why do we not continue exploring after the goal? I think we should not produce any children if we have already found the goal. So if visit and not goal reached, or reached goal, we are checking for the goal afterwards, but we can do it before. So if we have reached the goal, we're not going to expand anything. Maybe I'll just put that condition. Maybe I'll put that condition in the top. If not reached goal, then we're going to expand. Okay, run it again till the very end. And it only found one way to do it, and that is not really correct. I'm not sure why. Maybe it's because we visited a key. I see what's going wrong. So, no. I'm not sure what's going wrong. Let's run it again. So we are going to do always wait step by step, and we see what's happening. We have two paths. And once we reach the goal, we're not expanding anything at all anymore, even if, no, reached goal is not a global variable, it's local, it's very much only scoped for the current iteration. So why, when we reached our goal, can it be that we're not adding the target position because we already have a better solution? For example, one where we have more keys in that direction. Let's see how many visiting options are left after we reach the goal. Maybe we can do that just when we print. Right here. Like here. So the number of found keys are shown. And then we have a number of options left. And that is the length of... Can we do length? Not sure anymore. I think I am doing length. Yes, the length of to visit. So let's run it. Actually, let's run it here in debug mode. And then let's run it always. And two positions are left. Yeah, of course there's always only one other position to try. So wait a second, let's say we reach the goal. So that's almost here. So we are backtracing on the right, that is okay. And then we're backtracing all the way. And why is our other option not there anymore? I think it's because we already figured out by this point that you need to get D first before you're passing onto the other side. And I am going to make my console font a little bit bigger. Maybe like 18 again. Give it a bit more space. Let's just restart it. And we're going to wait always. So when there's one position left, it means that we still keep exploring. We've been through A and we took B, then we need to go first right, because that's the only way to do it. Okay, I didn't realize there was a door on the right side also. And then to go anywhere else, we first need to get C right. And then the question is, do we go to D right away or not? And then we have two options. And like that. And then on one side we're going to reach C. And on the other side we're still going towards door D. We can actually decide to go after E and then go back to get D right away, or to first open the door. So those are three options. And the first option opened door E, the second option goes back to get key D, and so that means there are only two options. One was getting E, getting D, and then going to the door for D, or going first through door E before getting door key D. Wow, that is very confusing, most likely. So there are two options, and So in one option we already have D, and in the other one we are still trying to reach it. And so now we have all of the keys in both cases, except one also has key E already. And so this is the one that went to get D first, and this is the one that went to get D later. And it's still not so clear which one is going to be faster. And it looks now, again, we have three options to get the key for door D after visiting door E or not. So those are three options. And we have estimates for how long that's going to take. Let's see. Okay, and now it looks like we tried everything, and I'm not sure why it stops. Maybe it's because we did reach a goal or something. I think that there might be something wrong. We do get an answer, and what is the answer actually? It says that the shortest path for this one is 86. Okay, actually it was just correct, so there was no problem at all. So example 3, that is this one, and let's run it on example 3 and run it, and let's go till the very end. 132. That is also correct. So I think my implementation is really fine. It's just a matter of that it's going to be very slow. It's going to take a long time. Example 4.txt. Trying that one. That takes, oh, we're running it till the end. And there's 81 steps, and that is also correct. So let's just run it on the input. And we're going to replace the file again with input.txt. Just run it. That's all. Have you checked sample 4 already? Yeah, I did. Wait, there are only 4 examples, right? This one, this one, this one, and this one. And I did check example 4 here. Let's do it one more time to be sure. Maybe I haven't checked it correctly. But you can see here on the right. Oh. Hey Crespel, you're stuck with the third one with equidistant keys. That's what you're stuck on, whichever that one is. So if you count this one as the first one, and your second and third, I think you're talking about this one, right? I haven't even looked at it. Maybe I haven't tried that one. Yeah. Example 3. Oh, I think, okay, I'm not sure which one that is. Let me just run it. Example x.txt. Example x. So that looks like this, and let's go to the end. And what do we get? It seems to run for a very long time. That means it's slow. Okay. That's kind of okayish, but I want to know what's going on. So let's always wait, or maybe till the next key. So it went there, and there, and there, and then there. I think the number of options is just growing and growing. And yeah, we have no kind of heuristic to know which key we should really try to reach first, and right now I'm always trying to reach the most nearby key. I think what we kind of need is some sort of pathfinding first to the nearest, or to all the reachable doors and all the reachable keys, then check which doors we can open. No, we need to know all the reachable doors that we can open technically, and then decide between getting keys and the next doors. So it's still running right now, and I think the combinatorial explosion is just too big, but we cannot solve it with a single A* algorithm. unless you're doing it in a different way. Well, first I was saying that you can just add up all the distances to the keys that are nearby you, but that's not working because they might be near each other and you can just kind of pass them all at once. That means, yeah, you wrote a system to find the requirements for any given key and work backwards from there. But this particular one is difficult since the best path requires going out of your way to grab others along the way. Indeed. Yeah. So now that I see that my algorithm is crazy slow on this simple example, I am going to decide to implement it in a different way, and I won't have time to do that now. So let's end it here pretty soon. Just gonna run it again without debug mode, but in normal mode, and see if it is any faster at all. And I think there might be like minor optimizations that I could do, but I think the bulk of the computing time is in the algorithm itself. So I think I really should rethink my algorithm, and that is going to be the estimation function that I need to update. Yeah, and I think what we could do is to basically keep a list of distances for every point to the next point or to another point. Like, what if you wanted to reach this position from here? How many steps would it take you? Something like that. And which steps you have to take, and are there any doors on the way? Maybe that's the way to do it. Making paths from every position to every other one, that is going to be a huge array, by the way. I think that's not something you want to do, no. Okay. But we could like make some kind of array where we keep track of every position and which doors you can reach from that position or something, or which keys and how many doors are on the way, something like that. But yeah, it seems really slow now, and it's not actually, yeah, it probably will complete, but it's just going to take too long. I run it till the end. Yeah. It's a very cool problem, and it's a competitive programming thingy. Yeah. And it's nice that in this case you really have to think about the algorithm, and it's intuitive. I like that. It's much more intuitive than day 16 with all of the numbers. I don't like number puzzles that much. And here you can really like think about it visually. So I like it also. Yeah. Emily, you're also still working on part 1, I see. This is a tough one. Okay, I'm going to end right here and try to finish later. I don't know, I'm starting to run behind. I already am behind on 16 and I'm behind today. So, right. I'm not sure if I'm going to be able to finish all of the puzzles. I do have a day off tomorrow, so I do have a bit more time. But we'll have a look and see. So thanks everyone for hanging out till the very end. Good luck on solving everything, and maybe tomorrow we can have a look at some of the code that Alex made, or Canyon Archer or Hans, who also solved it by now, if we have enough time for that. So see you next time. Bye bye.